Problem sheet 5, question 5. Cardiff University needs to create its exam timetable. It has a set M of exams, indexed by M, to schedule. For each pair of exams, IJ, it has an indicator, CIJ, that is set to 1 if modules cannot be scheduled at the same time due to sharing students, and 0 if they can be scheduled at the same time. Let T be the set of time slots available, indexed by T. Formulate a linear programming problem that finds a feasible schedule using the least time slots. You are not asked to solve the linear programming problem. Okay, so we have a formulation problem here, and we don't have any numbers, we just have some parameters, so we can build a general exam scheduling problem for Cardiff University and they can put their own numbers in. So first of all, let's define some decision variables. We care about whether an exam is scheduled on a particular time slot or not. So first we're going to let xmt be a decision variable. This decision variable will be binary. So binary means it can either take the value 1 or 0 and no other value. Why is that useful here? So we're going to let xmt indicating whether the exam M is scheduled on time T or not. So that's what an exam timetable is. It's just whether an exam is scheduled at a particular time or not. Okay, now that isn't enough for this problem, because if we think about what would our objective be, our objective would be to find a schedule using the least time slots. So we also need to know how many time slots we are going to be using. Now, we can't just use these XMTs because how many of those XMTs are going to be set to 1? Well, there's going to be M of them. There has to be, because every exam needs to be scheduled. So counting up the XMTs only tells us how many exams are scheduled and not how many time slots are used. So let's introduce another decision variable. YT be another binary decision variable. And there's only one of those for each day because it's indexed by T, and that is going to indicate whether a time slot T is used or not. Because if some modules are scheduled in the same time slot, which is ideal, is what we want, then this number will be smaller than M. Once we have these, we can start thinking about our linear programming problem, which will consist of an objective and some constraints. Now, our objective would be to use the least amount of time slots possible, so we can represent that as minimize the sum of all the YTs for every T in our set of time slots T. And we have some constraints. The obvious first constraint is that every exam should be scheduled once and only once. So for every module in the set of modules, then if we sum up over all the time slots, whether that module is scheduled in that time slot, the sum of all those should be equal to 1. That should indicate that only one of those time slots is used for that module, because these XMTs can only take the value of 0 or 1. So if the sum of them is equal to 1, only one of them is used. We also have a constraint that some exams have clashes. So if an exam has a clash, then they cannot be scheduled at the same time. Let's consider two modules, I and J. If we sum up XIT and XJT for a particular time slot, that is either going to be 0 if none of them are scheduled in that time slot, or it will be 1 if only one of them is scheduled in the time slot, or it can be 2 if both of them are scheduled in the same time slots. Now, if both of them are scheduled in the same time slot, that's a problem. So we want this to be less than or equal to 1. We want that to be less than or equal to 1 only if they clash. So the parameter Cij is 1 if they clash and 0 if they not. So if they do clash, 1 times that sum will just be that sum. And so if they do clash, we don't want that sum to be 2, so they need to be less than or equal to 1. If they don't clash, then Cij is equal to 0. So then we have 0 times whatever. That could be 2, it could be 1, it could be 0. But 0 times anything is 0, so that's always going to be less than 1 anyway. So if Cij is 0 and they don't clash, this constraint does nothing. But if they do clash, then that is saying that 1 times by that sum cannot be 2. And that's going to be true for every time slot, but also for every possible pair of modules. For every pair of modules ij in our set of modules. There's one other thing we need to consider, and that is how do we relate xmt and yt? We want to make sure that we are setting yt to be 1 if at least one of the xmt's is 1 for that time slot, and that yt is 0 if none of the xmt's are 1 for that time slot. How do we consider that? Well, for a particular time slot, the number of modules that is scheduled on that time slot will be the sum over all the modules xmt for a particular time slot. That'll be the number of modules scheduled in that time slot. Now we cannot compare this to yt directly because yt, remember, is a binary decision variable. So, and this expression here, the number of exams, can be any integer. So that can be above 1. So we can normalize this to be between 0 and 1. Now what's the biggest value this could possibly take? Well, that would be if all the modules are scheduled in the same time slot. So if we divide this by the number of modules, then this expression here should be something between 0 and 1. 1 if all the modules are scheduled, 0 if none of them are scheduled. Consider our objective function, the sum of the yt's. We are trying to minimize that, so it would be natural to try and put these as close to 0 as possible, or to set them all to 0. So we just need a constraint which will force a yt to be 1 if this expression here is bigger than 0. Like this. So if the proportion of modules scheduled at time slot t is 0, then yt can be 0. But if the proportion of modules scheduled at time t is anything above 0, then yt is forced to be 1. And finally, we have that x, mt, yt are binary for all modules m and time slots t. And this would be the linear programming problem for the exam scheduling problem. Let's consider how many decision variables and how many constraints we have. We have 2 sets of decision variables. xmt, how many of those are there? Well, there is m by t of them. yt, how many of them are there? There are t of them. So the number of decision variables would be mt plus t. How many constraints do we have? Well, this constraint here, that is a constraint that's true for every module. So there are m of them. This constraint here, that is a constraint for every pair of modules and for every time slot. So this would be m squared t of them. And this constraint here, how many of those are there? There are t of them for every time slot. So the number of decision variables is going to be mt plus t, and the number of constraints is going to be m plus t plus m squared t.